There's a novice pilot whose aircraft is about to crash. The aircraft is flying north and then takes a straight nosedive towards the Earth. Give the orientation of the nosediving aircraft in Euler angles using 3-2-1 transformation relative to the inertial frame, Fe, and using 0 yaw. So let's put in this coordinate frame attached to this aircraft. This is the inertial frame, so down is positive, north is out the nose, and east is out the right wing. So let's write out our Euler angles. Phi, theta, and psi. Psi is the one in the very top. So the aircraft is nosediving, so it has to be going straight down. So it takes a 90-degree pitch angle turn about the east axis. And it's negative because if you put your thumb in the direction of the east vector and you turn your wrist to do a nosedive, you'll cause a negative moment around the east vector. So that is a negative pitch angle.
Okay, part B, true or false. By introducing a negative elevator deflection, the pilot can save the aircraft and avoid crashing. Justify your answer.
This is true.
Negative elevator deflection leads to a positive moment, so the tail moves down and the nose rises. Okay, problem number 2. A small drone is flying with air relative velocity VB equal to this vector. The wind suddenly changes, and the moving velocity is that vector. So the wind here, written in E, inertial wind, expressed in the body frame. In response, the drone's autopilot adjusts the throttle to decrease the airspeed by 8 meters per second, and changes the drone's slide slip and angle of attack to maintain a stable flight. True or false, the autopilot can maintain the same v, which is the y component of the velocity vector expressed in the body frame of the drone's velocity, by adjusting the side slip angle b when the wind changes. If false, justify your answer. If true, what is beta in degrees? Here we have the inertial frame fixed to the body of the aircraft. So, we are given the velocity of the aircraft expressed in the body coordinates. So let's write these components out. And it's a column vector because it's transposed. And these components are equal to u, v, w. And they also give us the inertial wind in the body frame. And let's make this reminder for ourselves that there is a change in velocity of negative 8 meters per second, because this will affect the airspeed later. And this is important because the velocity expressed in the body frame depends on the airspeed, as you see right there. And we're trying to find beta, so we need to rearrange that equation for beta. So now let's find the airspeed. Airspeed is the magnitude of the velocity in the body frame. So we have those components, so we'll just take the square root of each of those. We'll square each of those components and take the square root of all of them. We get 166.02 meters per second. So let's plug that into our equation, but we cannot forget about that change in velocity that the pilot did to maintain stability. So let's subtract that from airspeed. We get 0.47 radians, but the problem asks for it in degrees, so let's convert that to degrees, 27.04 degrees. So it is true that the autopilot is capable of maintaining the same y component of the velocity expressed in the body frame, which is v, by adjusting the side slip angle when the wind changes. So now we're just trying to figure out, okay, can the autopilot keep v, the y component, and the x component u constant by adjusting both the angle of attack and the side slip simultaneously? So I'm going to write out this expression that we'll need again. We used this expression in the previous part. It's the velocity expressed in the body frame. Each component, the x component is u, the y component is v, and the z component is w. That vector is equal to the airspeed times this vector using alpha and beta. So we want to keep alpha, we want to find alpha and beta such that u and v are constant. And we know u is equal to that. So u is equal to this expression, and I'll show you where I get this. I just take the top row, and it's one expression. So now I'm trying to find the airspeed. We found that previously in the previous part. Just making a note, that's after the change in velocity of -8. And we know that before, to keep the y component constant, this beta needs to be equal to what we just previously found, which was 0.473 radians. Now let's plug that in. We know what u is, we know what VA is, and we know what beta is. Let's solve for alpha. Is it possible that alpha exists such that u and v can stay constant? And alpha equals cosine, the inverse cosine of that number. And if you plug that into your calculator, that does not exist. So the answer is false. Okay, part C. What is the drone's final ground speed if the autopilot sets alpha equal to 5 and beta equal to -3 when the wind changes? Let's write out our new information that we just have. We're trying to find for the ground speed, and we get these two angles. So, without wind, the velocity expressed in the body frame is what they gave us. And that's equal to UVW. And that's equal to the airspeed times this vector. That relates the angles, so we can use what they gave us. Now, when there is speed, we have to use this expression. And the airspeed is equal to the magnitude of the velocity. And the ground speed is equal to the magnitude of the inertial velocity. So that is the ground speed, the magnitude of that, and the magnitude of this is the airspeed. So the airspeed is equal to the magnitude of the velocity in the body frame. So that's equal to what we found before. So right here we're using the expression for the velocity expressed in the body frame without wind, and plugging in all the angles. Now we are finding the inertial velocity, taking into account the wind. So let's put the first vector in and add the wind. And that's what they gave us for wind. And doing this vector math, we get this vector. But we're not done yet. We need to take the magnitude of that vector for the ground speed. which is equal to 162.4 meters per second. So that's our answer. Alright, last problem. Consider an aircraft with an inertial position expressed in inertial components as a function of time. And the orientation is also a function of time, given by phi of t equals 10 degrees, theta of t equals 10 degrees, and phi of t equals to negative 5 times t degrees. What is the angle of attack of the aircraft at time equals 5 seconds if there is a constant wind, background wind? And make note of this, this wind is expressed in the inertial frame and written in the inertial frame. So they gave us the position in the inertial position expressed in the inertial frame. So that is good. That matches the expression of the wind. Additionally, they gave us these Euler angles with respect to time, and they want us to find the angle of attack of the aircraft at 5 seconds. So I plugged that in to the psi angle to get the psi orientation, the yaw orientation at that time. Let's also write out the inertial wind vector expressed in the inertial frame. And what is the angle of attack at 5 seconds? That's what we're trying to find. So the derivative of this position vector can be just simply the derivative of its components because the inertial frame is not rotating, so we don't need to use the transport theorem. So that's just the derivative of each component of P. And this is an expression that takes into account the presence of wind and the effect of the velocity vector after wind is included. That was the general expression, but let's relate it to the frames of our problem. So the velocity expressed in the inertial frame, which is equal to the derivative of the position vector written in the inertial frame and expressed in the inertial frame, minus the wind vector expressed in the inertial frame, the inertial wind expressed in the inertial frame. So that's the position vector, the derivative of the position vector, and that's the wind vector that they gave us. And these are all expressed in the inertial frame, which is good. And just to recall, this is the derivative of the components of the position vector. Because Fe is not rotating, we don't have to account for the rotation of the frame additionally. So just plugging in 5 to that, this is what we get. Simple multiplication and addition here. Okay, so we actually need the velocity expressed in the body frame. That's what they're asking for. So we need to rotate the velocity written in the inertial velocity expressed in the inertial frame that we just found. By this we need to multiply it by this rotation matrix. So we're going from the inertial frame to the body frame. So our new velocity vector in this new frame is equal to the rotation matrix from our old frame to our new frame multiplied by our velocity vector. So this rotation matrix, it needs the Euler angles that they gave us above. So let's just take those and put them right here. And that's at 5 seconds. That's why it's negative 21 for psi. So this is the rotation matrix from E to B. Frame, the inertial frame to the body frame. I am writing out every step so explicitly because I don't want there to be any confusion. That's the rotation matrix. And the velocity defined in the inertial frame, expressed in the inertial frame, is what we found before by taking the derivative of the position vector that they gave us and plugging in 5 for time. So now we do matrix multiplication. We get this. Amazing. And the first component is the velocity in the x direction, second is the velocity in the y direction, the third is the velocity in the z direction with respect to the body frame. So the plane could actually be going upwards even though it has a negative z velocity because you don't know what the plane's orientation is, but we actually do, so you could figure that out if you wanted to. Okay, now for the fun stuff. Finding what they actually wanted us to find. The angle of attack. So this is the expression for the angle of attack using components of the velocity vector, the inertial velocity expressed in the body frame. That's why we needed to rotate it, because alpha is defined using the components that are expressed in the body frame. So the z component of the velocity is w, and the u component is the velocity in the x direction. So w over u. And alpha equals negative 84.6 degrees. And this makes sense because alpha is measured from top down. So that just means that the alpha is being measured the opposite way. So it's going above the velocity vector. So it could be ascending, but it could not be also depending on its orientation. So you would have to look at that. And as I just showed, the angles were given in degrees, so we give our answer in degrees.